welcome back. So, this lecture we are going to talk about fully digital current mode control architecture. So, first I will show you a custom MATLAB model development for fully digital current mode control, and then I want to consider few simulation case studies. So, first we will start from fixed frequency mixed signal peak current mode control, because that we have discussed in the last class, where we have considered the analog current loop and digital voltage loop. Now, if you go to fully digital current mode control, then we also need to sample the inductor current. That means we have already sampled the output voltage here, but we also need to sample the inductor current. And we have discussed there are two possibilities. If we sample the inductor current, because we need to retain the ripple information of the inductor current. So, one way you can use a very high sampling rate for the current loop, but that may not be preferable because that will actually incur more losses and you need a very high sampling or high speed and A to D converter. But rather is more kind of effective way if you can sample once per switching cycle and emulate the ripple of the inductor current internally using the digital control platform. That means, but it is not necessary that we need to generate the same rising slope of the inductor current. It may be different, okay, but we are trying to emulate this current ripple inside the digital platform, and we are taking sample of the inductor current once per switching cycle. So, how to start with? So, we want to repeat the same process, the A to D converter that we have discussed for the voltage loop. It has sampler, quantization and the delay, and we have already discussed that whole A to D process can be divided into this event triggered sampling followed by quantization, and you can add one additional delay also. Next, this part we have discussed, and in fact we have discussed for multiple lectures. We have also discussed how to implement a PI controller. In fact, in the previous lecture we have discussed that if you want to implement a PI controller using difference equation, not by transfer function, then it has to be clock synchronized. And if you go back to the MATLAB file, that means this is a fully digital peak current mode control. So, this part also we have discussed. That means we have used a trigger pulse to synchronize. That means this is used to generate ui n minus 1 from ui n. That means one cycle delay of the integral output, and that is synchronized with respect to the trigger signal. Similarly, but after that trigger previous, that means ui n minus 1 which is coming here, it will be added along with the ki into error voltage. So, kid means discrete time integral gain into error voltage. So, this is the overall integral controller. That means ui n is equal to ui n minus 1 plus kid into vn. So, this is the integral controller implementation, and this is the proportional control implementation, and this output is actually used here. So, that means this is the output of the integral control, this is the output of the proportional control, and if you sum them you will get the PI controller output. So, this part also we have discussed. That means it is not simple transfer function, we are using a difference equation with a clock synchronized operation. Next, this part is very important, because here we are not using analog current loop, we are using emulated current. That means, let us first start with the basic concept. If you sample the inductor current, let us say this is our blue one is the actual inductor current. Okay. Now, this is the sample of the actual inductor current. That means we are sending the sampling command, that is the point we want to sample, and generally this sampling point is slightly earlier than actual switching takes place, because if you go to any current sensor, right, so you will find the spike in the current sensor, the switching spike, once the switch turns on or the switch turns off. So, every time, that means I am talking about this is the actual inductor current, but let us say if you go for any sense inductor current, then you will have switching spikes here after the switch turns on and off. So, in order to avoid such spike, so we want to sample just before the switch either turn on or turn off. So, in this case we are talking about the trailing edge modulation. So, we are taking the sample here. That means where this is the sampling point. This is just below the switch is about to turn on, that means it is the off state. That means you can say it is a valley current. Now, that means we are sending the sampling command here, but as I said that A to D converter require time for conversion. That means we cannot get any immediate sample available for the controller, because we need to add this sawtooth waveform, the RAM I will discuss, but we cannot use the current sample for the running cycle because we need to provide some time for A to D conversion. So, that is why the sample command is sent here, but the actual current sample is used in the next cycle. So, there is an inherent one cycle delay. So, that means this is the point of sampling here, but the availability of the sampling, including we are forcefully delaying for the safe side, because we need the information of the valley current, because we cannot actually take any other point, because we need to take the valley point. So, we are using that valley current information in the next cycle. And you can see this particular waveform indicate the sawtooth waveform that is actually used inside the digital controller. That means, if I want to draw, let us say this conceptual point. So, suppose I am just taking, let us say I am just considering the inductor current like this. Okay. So, this is the inductor current waveform. Now, we are actually sampling the current here, that means we are just sampling just before switch turns on, but we are using this sample in the next cycle. That means this sample, this if we just interpolate this sample, if we extend here. Now, we want to add a RAM, that means we want to create a sawtooth waveform here. This is the addition, that means if I take, this is my IL n minus 1, and if this sample is IL n, and if this sample is IL n plus 1 and so on. So, we want to add a RAM. So, sawtooth waveform means it is like a staircase implementation, and if we take a very narrow staircase, it will be like this. That means, if we want to, that means whenever we start switching, at this point we are using a different color. Let us say we want to start, this slope may be different, this slope may be different. 1 minute. So, this slope should be different, and why we are going up to this, because here we have to turn off. And how it is turned off? As if there is a peak current reference that is coming here. When this hit the peak current, then turn off, and since we are using a counter, we will simply reset this, because we are using the counter. And why we have reset it? Because we want to, after this there is a latch operation, it is a trailing edge modulation. The switch we cannot change state, that means once the switch is turned off, the switch cannot turn on throughout the rest of the interval. So, it has to wait for the next clock edge. So, that means it is not necessary to extend this waveform beyond that, or we do not need to emulate the falling slope for peak current mode control, because that information is simply redundant, we do not need that. So, it simply resets it. Next time, now this sample point is extended. So, this sample point is extended here, that means we are using this sample point, is extended here, but our sawtooth waveform, our ramp signal, that means this will start from here. Again, it depends upon the peak current. So, that means you can see this waveform, that means if I rub up all this part. So, you can see the sample of the inductor current is used in the next cycle here, and with an added ramp. Although it looks like the ramp is same as rising slope, but it is not necessary, the ramp can be different. In fact, there are many research that this ramp should be different, and we cannot keep this M1 slope because it will be unstable. Even this MC requirement, when I will go to the analysis part, it can be shown that the MC has to be greater than M1 plus M2. That means M1 is the minus M2 is the falling slope of the actual inductor current, and M1 is the rising slope of the inductor current. So, this MC has to be greater, otherwise it will be the inner current loop will be unstable, and that can be proved. But what I am showing here, that you need to add RAM, okay, to emulate this current. Now, so I think the basic operation is clear. We have to take the sample of the inductor current, we have to delay by one cycle, and then we have to add the compensating. So, compensating RAM, or basically the emulated RAM, is always added in every cycle, but only thing its base point depends, because the if you say a counter, let us say if you say a counter which generate this sawtooth waveform like this, the output of the counter should be added with our sample current, whether it is a ILN plus 1, it will be updated. So, that means the base value will be changed according to the value of the inductor current sample. Okay. So, that means now, so how do you generate this sample inductor current? So, this is, we know we can simply use a to D converter block, and that we know, event trigger ADC, but we need to delay by one cycle. So, you would another. So, if you simply use this current, this is the actual inductor current which is shown here, and this current is shown here, this is sample current. You see, it is taking the sample of the current, just it is updating, but we need a realistic current sample for the controller, because this sample may not be available immediately. So, we need to use another such block which will delay by one cycle, and if you see one cycle delay, so this waveform is the green waveform here. So, that means we are generating, first block will generate the sample and hold of the current value point, and the second block will delay by one cycle. So, this is the overall implementation of the sample value, but it is not sufficient, because we have to add this RAM, because after this sample point we have to add this RAM. That means we need an additional block of this. And how to generate a ripple emulator? So, that means MC, and we are only activating this MC because it is just for MATLAB programming, but if you use an FPGA or any digital controller, you have to use this sawtooth waveform, right. So, it can be a simply counter, and it will start counting when the clock signal comes. That means at every rising edge of the switching clock, that means when the switch is turned on, this will keep on incrementing, and whenever, that means this clock, this ramp output plus the sample current is added, when it hits the peak current, then it is reset. So, that is why there is a reset signal. So, that means reset will happen when you take the Q signal, that means when your switch goes low, that means this is the gate signal, when it goes low, that is actually reset the counter. So, it will just stop, and this is the overall current controller that is used to, that means, and now this ramp here we are using simply integrator, it will integrate, you can reset, but in actual implementation you can use a counter. Okay. So, actual ripple emulator. So, this is the overall diagram which realize our error emulator block. So, this is a fully digital current mode control architecture, and we want to go inside, that means the MATLAB block, and that I am going to consider. So, everything else is same, only this controller is different. Here again we are taking output voltage, reference voltage and the inductor current. What we are doing here, and for simulation we want to verify, we want to check how the emulator signal, emulated ramp look like, how the reference current look like, and you can also see the sample voltage. So, all are captured into the workspace. Next, if we zoom this whole block of this controller, so it start with this, you can see the, that means if you take this output voltage, this is number 1, number 2 and number 3 input port. So, number 1 input port is this, number 2 is the reference, and number 3 is the inductor current. So, this block is our, what is this block? This is your ADC for output voltage, for output voltage sampling. Okay, it is for output voltage sampling, ADC for output voltage sampling. Next, inductor current. emulated RAM as well as the sampling block, that should be inside, and this is the PI controller. Okay. So, if we go to the next, this is the inside the error, because what it is generating, IE, which is the emulated current, which include sample current plus the emulated current, and that will be compared to the reference current, and the reference current is coming from the PI controller. So, now we want to go inside this block. That means we are talking about this block, and this block is shown here. What is the input to this block? Input to this block is the number 1. So, you can see what are the input to this block. That means input to this block is the inductor current. Yes, this is the inductor current, and then gate pulse. So, gate pulse, these are 2 input. Okay. Next, so this is the first conversion, that means this is the ADC for inductor current, and this is the event triggered ADC, and this is used for 1 cycle delay. And now this is our sample inductor current. Once we get the sample inductor current, and this is our sawtooth slope MC. So, you can set our whatever we want to use, that you can customize during runtime as well as you can customize in the .m file. Then when the gate pulse is high, then only this will come, and when this comes, this is a scaling factor. That means output of this block will be MC when the gate pulse is high, and this will be used for resettable subsystem which has an integrator, and I will go to the MATLAB block to show. So, now this will generate our that sawtooth edge, that means a continuous waveform, and with which we have to add the sample inductor current, sample plus delay, that means the 1 cycle delayed sample inductor current, and then overall current is the emulated current. So, if you go to the MATLAB, let us go to the MATLAB. Here you can see this is a controller block, emulated RAM block that we are discussing. So, if you go to resettable block, there is a resettable integrator. That means the integrator generally, if it is reset, otherwise the integrator will keep on increasing. Okay. And who will reset the integrator? The integrator reset happens, that means based on the gate pulse. That means the gate pulse, it has to, there will be edge, the edge detection circuit, and when you detect this edge, so this is an edge, resettable edge, so it will detect the falling edge, and that falling edge is used to reset the integrator. That is it. Next, the constant, that is the slope of the current that we want, and output, and this is the A to D converter for sampling ADC, this is for 1 cycle delay, and this is actually added here. So, you can see this block and this block are same, go to block and the form block, and this will generate our actual emulated RAM. And I want to show you actually all the waveform, but before that I want to explain the remaining part. Next, this is a PI controller. So, I am talking about this block is shown here, and this we have discussed. This is exactly same as mixed signal current mode control, where it is a PI controller, and it is a clock driven PI controller which is implemented using a difference equation. And again this is used to generate what? If the input is ui of n, then output will be ui of n minus 1, and that is actually added here, and then this ui of n is generated, which is ui of n minus 1 plus ki into Ven, and this is your Vn, and this is your proportional controller, and this output actually goes here by this block, and this is the overall. So, this is a PI controller output, Okay. So, now let us go to the MATLAB and try to understand. So, we will simulate few case studies. So, in this I want to first if I go to the MATLAB, I want to show a peak current mode control with a delay, where we are using again a load transient and we are not using a very large gain. So, let us first run the simulation and I want to show you all the signals. Okay. So, first I want to show the output voltage waveform, and if you see the output voltage waveform, you can see. So, here I am not showing any delayed version of the output voltage, because if you add delay, you can add it, you can customize it based on the requirement, but I want to first try to show the basic implementation of fully digital current mode control, where there is no need to consider delay. So, you can assume that output voltage is sampled exactly at the switching point or just below before that, but one can go, because if you go to delay, there will be more advanced level analysis, will be very complicated and is a research topic actually. So, then next part I want to show the current waveform. So, let us go to the current waveform. If you go to the current waveform, the first thing I will show, so if I take one complete cycle, so you can see the blue one is the actual inductor current, which is like a sense inductor current, and the red one is the emulated slope, that means which is much higher, otherwise it will be unstable. I will show you. And after adding the sample with the emulated slope, actually you can see here under steady state, when it reaches under steady state, since the valley point is exactly like repeating every cycle, then it will look like as if like a sample and then added the ramp. But I will show you the transient case also. But if you take a transient case, I am just showing, I just want to emphasize, you can see that let us first consider maybe here, yeah, you can see this point, this is the inductor current for this cycle. For this cycle, the valley point of the inductor current is here. So, you can interpolate and this is a valley point. That means your ramp is added, that means if I further zoom this cycle, this point is interpolated here and then we have added this slope. That means if you carefully observe, we are making one cycle delay. This is your actual inductor current and its sample is used in the next cycle, and then we have added that MC, and after MC this is a emulated ramp plus sample current when the overall current is compared with the peak current. When it hit the peak current, then switch is turned off, and that is exactly what we have explained. That means if you try to understand this part, so if you go this block, take few cycle. So, inductor current, this sample is used here and we have taken a very large ramp. So, because otherwise it will be unstable. So, let us say it is 2.1 type. So, if we use a ramp, let us say 1.5, and we want to see it is the Vn by L, we have taken a more conservative slope, much more conservative slope. So, although it is stable now, the slope of this even higher, but again this operation I am showing. Now, suppose if I want to say, let us say what is the rising slope of the inductor current, it is something like a Vin minus let us say Vref. So, let me check, yeah, it is Vref. So, suppose I am taking just V in my inductor rising slope 1.5 times, will it work? Let us see. It is still working, but it is slowly going into, so it is still working. That means we have used the slope, if you see, just 1.5 times. But suppose if we make it just the same or maybe 0.01, just slightly above, it must be unstable, that I can show, and it is actually unstable. You can see there is a subharmonic instability that are coming because the current loop is unstable. And when you go to the analysis part, it will be shown that you need, this is nothing but M1 plus M2 plus, that means the MC should be greater than sum of M1 plus M2. M1 is the rising slope, that means if we go to, let us say, what is that means, that will be discussed in the theory. That means I am saying the MC should be greater than M1 plus M2. And in a buck converter, what is M1? It is Vin minus V0 by L. And what is M2? It is V0 by L. Then what is M1 plus M2? It is simply Vin by L. So that's why we have taken, if we just MC is above Vin by L, then it should be stable, and we are going here. That means initially what we have considered, if we just take Vin just 1.0 time, this is a verge of very close to instability, we are considering very close, it is even unstable. And I will show, I mean it actually a research paper, there are research paper when you go to analysis, even this, even if you make it higher, it is not enough when you close the outer loop. And again these are research topic, but I can say that we need to take sufficiently a conservative choice of this, so that it will be stable. So you have to make sure the current loop closed, because if we increase, and you can see it is stable, it is stable. But suppose if we make this controller, if we make 60, that means we have increased the controller gain, and see what happened. Is it still really stable? So it become unstable. That means the choice of this slope also depend the closed loop, and there are research paper, but again I am not discussing, I am just showing that you need to be careful about this design. And we are not going to consider design of full digital car because this is a more advanced topic, but it gives you some kind of motivation that this is a very interesting problem, and you have to be careful about the selection of outer voltage loop, otherwise you will end up with instability. So you can also perform, here I did load transient, you can do reference transient, and you can carry out the same reference transient that we have performed for mixed signal current mode control. Okay, but because there is a on sample delay, you can see there is some kind of oscillatory behavior, because any delay will actually cause phase margin, I mean degrade the phase margin, and because of that poor phase margin, it will also become more oscillatory. Okay, so we need to be careful about this design process. Okay, so in summary, we have discussed custom MATLAB model development for fully digital current mode control, and we have considered few MATLAB simulation case studies. So here we want to finish the fixed frequency digital current mode control implementation. In the next lecture, we are going to talk about variable frequency digital current mode control. So with this, I want to finish it here. Thank you very much.